Good afternoon, class. Here's chapter 3, derivatives, section 3.3, basic differentiation formulas. So we covered derivatives and rates of change, derivative as a function, and now basic differentiation formulas, reminding everybody, if we have a function y equals f of x, and we connect 2 points, we can calculate the slope, rise over run. Delta y over delta x, y sub 2 minus y sub 1 over x sub 2 minus x sub 1, or f of x minus f of a over x minus a. Or if you look at this case, as we go from a to a plus h, the run is h, and this is f of a plus h minus f of a is the rise. So that's the ratio, also known as difference quotient. If we call this point b f of b, therefore f of b minus f of a over b minus a. These are different ways of writing the same thing. As q approaches p, gives rise to the red line known as the tangent line. The tangent line is the limiting position of the secant line PQ. As Q approaches P, a tangent line is a line that touches a curve at a specific point without crossing it. Slope of a tangent line, also known as the instantaneous rate of change, we can take the limit of this piece as x approaches A, or this piece as h approaches 0, or just m of PQ as Q approaches P. We call it f prime of A, or the slope of a tangent line at x equals a. If you want to find the equation of a tangent line, there are 3 ways to write lines. Standard form, ax plus by equals c. Point slope, y minus y1 equals m times x minus x of 1. And slope intercept form, y equals mx plus b. By the way, slope intercept form is the only one that is unique. So we use this one, and we write the equation of a tangent line. Y minus y1 is f of a, m is f prime of a, and x minus a. Now, generally speaking, we call this a differentiation formula. F prime of x is the limit of f of x plus h minus f of x over h as h approaches 0. And again, this is the distance h. This is the run, and the rise is f of x plus h minus f of x. And we are making h to go to 0 as far as the limit is concerned. And now, let's look at basic differentiation formulas. We start with a constant, y equals a number, f of x equals c, or a number. And we see that the derivative is 0, and we look at it 2 different points of view. From the point of view of a graph, this is a horizontal line. Every horizontal line has a slope that is 0. So if you pick any number, y equals 5, 10, minus 8, makes no difference. You have the same answer, f prime is 0. From the point of view of the definition, because we want to prove that f of x plus h, if f of x is c and it's independent of x, then f of x plus h, or f of anything, is c. C minus c is 0. Bear in mind, we are taking the limit of this expression as h approaches 0. H is not 0, is getting close to 0, whereas the numerator is 0. Therefore, the answer is 0. So derivative of a constant function, d dx of c, equals 0. I want to remind you of the definition of the E we found in algebra, reminding you of the compound interest A equals P times 1 plus R over N to the power of NT. Now, if we let R over N be something, the reciprocal becomes the reciprocal of that. So if N over R is M, then R over N is 1 over M. Look at the cross product. N times 1 is R times M. So we're going to replace R over N with 1 over M. And we're going to replace the N with R times M, or M times R. And we separate this, and this piece was the definition of an E, and we went to the compound interest. continuously, and we said A equals P e to the power of RT. Therefore, if you look at this piece, E is a number such that it's the limit of 1 plus 1 over m to the power of m as m approaches infinity. Now, it's important to know the key is that these three must be the same. In other words, I can use any variable. If I said x, this is x, this is x. Also, let 1 over m be something, for example, h, then m becomes 1 over h. So we're going to replace 1 over m with h. We're going to replace the m with 1 over h. And when m approaches infinity, h approaches 0. So this is another expression that comes from here. So the limit, let me erase my word. The limit of 1 plus 1 over m to the power of m as m approaches infinity is the same as the limit of 1 plus h to the power of 1 over h as h approaches 0. And as you know, that's E is 2.71828, and it continues indefinitely. So we have these two, and again, notice what I did. I changed the m to n on purpose, and I changed the h to x on purpose. The point being, these three must be the same. These three must be the same. Now this, the limit of e to the power of h minus 1 over h as h approaches 0 equals 1. We're going to look at it in this section. So let's start with the power rule and see some of the rules that are used here. ddx of x to the power of n is n x to the power of n minus 1. Therefore, ddx of x must be 1. Just remember, the exponent is 1 here. So if we want to go with that, becomes 1 times x to the power of 1 minus 1, which is 1 x to the power of 0, which is 1. Okay. All right. Then we have more. Let me erase my work. The constant multiple rule. If c is a constant and f is a differentiable function, d dx of c f of x is c d dx of f of x. Meaning, if you have a constant, take it out. The sum rule, the derivative of the sum is the sum of the derivatives, assuming the functions are differentiable. The derivative of the difference is the difference of the derivatives. And now some of the formulas we come across. The derivative of a constant is 0. The power rule, the derivative of x to the power of n is nx to the power minus 1. The derivative of kx is k, where k is a number, is a constant. So, and again, comes from here, because the derivative of x becomes 1 and k remains. The derivative of e to the power of x is itself, e to the power of x. The derivative of sine is cosine. The derivative of cosine is negative sine. We'll look at the rest later. I'm going to quickly mention it. The derivative of tan x is secant squared. The derivative of cotangent x is minus cosecant squared x. The derivative of secant x is secant x tan x, and the derivative of cosecant x is minus cosecant x cotangent x. And now, we want to look at the proof of the power rule. We know when f of x is x to the power of n, f prime is n x to the power of n minus 1. But can we prove that? Well, you have to go with the definition. Starting with reminding you of some of this stuff from algebra, for example. In this case, if I want to come up with f of x plus h, I'm going to write x plus h to the power of n. So everything is very straightforward. This one, I want to make sure we understand x plus h to the power of n. Now, how do we raise this to the power of n? We use what is called binomial theorem. To know binomial theorem, you have to remember factorials. Factorial, n factorial is n times n minus 1 times n minus 2 all the way to 1. 0 factorial and 1 factorial are 1. For example, 5 factorial is 5 times 4 times 3 times 2 times 1, and that becomes 120. What is a binomial theorem? A plus b to the power of n is n choose 0. This is a combination of n choose 0. A to the power of n, b to the power of 0. N choose 1, a to the power of n minus 1, b to the power of 1. All the way to the end, n choose n, a to the power of 0, b to the power of n. Notice, the exponent n is the same for all combinations. From n, you choose something. You start with 0. Now, a takes the exponent n, b, the second one takes the exponent 0, they must add up to n. And this is the same as this one. When you go to the next one, this becomes 1. So you take 1 from n, give it to b. Okay, n minus 1 and b. They must add up to n. They must add up to n, and so on and so forth. An example of that, you may recall a plus b squared is a squared plus 2ab plus b squared. A plus b cubed is a cubed plus 3a squared b plus 3ab squared plus b cubed. Those are specific case, special case of binomial theorems for n equals 2, n equals 3. Also, reminding you, NR, and we write it as CNR, and also we write it as a parenthesis N comma R. It represents a combination of N choose R is less than or equal to N always. So it's N factorial over R factorial times N minus R factorial by definition. So for example, if I want to evaluate this one, I get N factorial over 0 factorial, which is 1, N minus 0 factorial, which is N factorial. So this is 1 N factorial, the answer is 1. So we know this is 1. And by the way, I'm going to leave it for you to show that this one is 1. What about N1? N factorial over 1 factorial, N minus 1 factorial. And notice, because we can change this to N times N minus 1 factorial, it becomes N. So this answer is N. By the way, it's something that probably you've seen. NR is generally speaking equal to N and N minus R. In other words, if these two add up to N, they are identical. That's why N0 and NN is the same. And again, we can show that easily. So with that being the case, this one is clear. What is x plus h to the power of n? We use this one. And again, n0, a to the power of n, b to the power of 0. Remember, b to the power of 0 is 1. So basically, this is a to the power of n. So again, I want to make sure that we understand that this thing is just a to the power of n. And this one is b to the power of n. So we're going to write that. And I'm going to erase my work. So the first one is x to the power of n. The next one is n, x to the power of n minus 1 h. And we go all the way to the n, which is h to the power of n. Now, and by the way, this one is n choose 2, just as it is here. And we don't even need to know what that is. You'll see in a moment why. First of all, this one and minus x to the power of n cancels. Secondly, what is left in the numerator? Each and every one of them involves an h. So if I take the h out from the first one, it doesn't have h. The second one, you write it with h to the power of 1. This one, you write nx h to the power of n, you're going to subtract 1, n minus 2, and this is n minus 1, because one of the h's comes out. Now it can cancel out the h. And whatever remains, everything has an h, this one, all the way to here. Limit as h approaches 0 makes everything goes to 0 except the first term. And therefore, when f of x is x to the power of n, we proved f prime, its derivative is n x to the power of n minus 1, known as the power rule. Let's use the power rule for these cases. Simply put, the derivative of x to the power of n is n x to the power of n minus 1. So put this in front and take it down by 1 notch. You get 6x to the power of 5. $1,000 sits in front, goes down by 1. 1,000 x to the power of 999. Same thing here, 4 sits in front, t cubed. And you can write it y prime or dy dt. I'm writing dy dt just to remind you, based on Leibniz's notation, we write it in this fashion. And what it indicates is that the independent variable is t. 3r squared Never mind the 3r squared is 2r. Okay, so 3 times 2r is 6r. The way you write it, dy dr, ddr of 3r squared, or simply y prime. Again, the advantage of the Leibniz's notation is that it does give us the independent variable. It tells us which one is the independent variable. Over here, 10 times 6, 60x to the power of 5 is the answer. So f prime of x is 60x to the power of 5. Over here, when we looked at the theorems that were discussed in the beginning, known as the sum and the difference rules, as you recall. So it basically means do them term by term. So we're going to work with the first one, 8x to the power of 7. Then the second one, 5 times 12, 60x to the power of 4. 4 times 4, 16, minus 16x cubed. 10 times 3, 30, plus 30x squared, minus 6, and 5, of course, is 0. So you do it term by term. That's the idea. F of x is 5x plus 1. Obviously, f prime is 5, and you're done. F of x is 2 over x. Reminding you of the exponential rules. And look at the negative exponential rules. I can write this as 2x to the power minus 1, get it ready for the power rule. So now I have 2 times negative 1 minus 2x to the power of minus 1, which is minus 2. And of course, this goes down, becomes x squared. So negative 2 over x squared. What about this one? 7 times 2, 14, and the exponent goes down by 1, becomes 14x. First, we change square root of x to x to the power of 1/2. Then we use the product rule. This has exponent 1. This has exponent 1/2. They add up to 3/2, and of course, this is 5x. Algebraic step. So we just used an algebraic step. Now we put the 3/2 in front, x to the power of 1/2 plus 5. And x to the power of 1/2, we put it back in the same format we had. So pretty straightforward, everybody. What is the derivative of pi squared? The same as pi, the same as e, the same as 1, the same as negative 10,000, the same as any other constant, any other number. The answer is 0. The idea is that don't get confused because it's pi squared, okay? All right, so what happens here, we're going to use our techniques of algebra to rewrite them. So 1 over x to the power of 5, as I mentioned, you go with the negative exponential rule, and you can write x to the power minus 5 to get it ready for the power rule. Minus 5 sits in front, x to the power of subtract 1. And so negative 5x to the power minus 6, bring it down, because we don't want to go with the negative exponent. So minus 5 over x to the power of 6 is the final answer. 2 over 7, x to the power minus 3. We are getting it ready for the power rule. Which means 2 over 7 times negative 3, x to the power of, now take it down by 1. So this is minus 4. So we have negative 6 over 7 x to the power of minus 4. This goes down, becomes negative 6 over 7x to the power of. This one, use the quotient rule, and we say 2 over 9 x to the power of 5 minus 9. That means negative 4. Getting it ready for the power rule, which means now I can differentiate this. 2 over 9 times negative 4 times x to the power of minus 4 minus 1, which is obviously minus 5. And this is negative 8 over 9 x to the power of minus 5, which goes down, and we end up with f prime being minus 8 over 9x to the power of 5. So pretty straightforward, everybody. So we're dealing with power rule, and things that they don't look at, we change them. For example, right here, we've already dealt with that. It's x to the power of 1/2. So it's 1/2 x to the power of 1/2 minus 1, which makes it negative 1/2, or 1 over 2 x to the power of positive 1/2, or 1 over 2 squared of x. And now, if you look at these rules, we're going to write this as 2x to the power of 4 over 5. We're going to multiply 2 by 4 over 5, and then x to the power of 4 over 5 minus 1. So we get 8 over 5 x to the power of negative 1 over 5, or 8 over 5 x to the power of positive 1 over 5. So f prime of x is 8 over 5, the fifth root of x. You put it in the same format. This one, you just make up two fractions. This is 10. This is minus 7x. So f prime is simply minus 7. Very straightforward. Very easy, everybody. Find an equation of a tangent line to the graph of the function f of x equals x squared minus 3x minus 1 at x equals. So we need two things. We need a pair x comma y, we plug in. We need the slope, we differentiate. So we differentiate f prime of x is 2x minus 3. If I plug into this one, 4 squared is 16. 3 times 4 is 12. 16 minus 12, 4 minus 1 is 3. That is the pair x comma y. If I plug it in here, 4 times 2, 8 minus 3 is 5. That is the slope. And I'm going to use the point slope rather than memorizing the formula, you can go with that. Y minus Y1. Y minus 3 equals M5, X minus X of 1, X minus 4. We get 5X minus 20 plus 3. So Y equals 5X minus 17. Very straightforward, everybody. Find the points for which the tangent lines are horizontal. So there are 2 points here. To find, as far as the tangent lines, that means you need the slope, you have to differentiate. So you get 3x squared minus 6x. As far as tangent line being horizontal, you know the slope is 0. You set it equal to 0. Okay. Now you factor the 3x out. And x is either 0 or 2. You have to realize you have to put this back in and you get 0, 5. And you have to put this one back in. And you get 2 cubed, which is 8, 2 squared, which is 4 times 3 is 12. So 8 minus 12, negative 4 and 5 is 1. So let me quickly show you. If I put in 2, I get 2 cubed minus 3 times 2 squared plus 5, which is 1. Okay, just want to make sure that it's all understood. Now, what are exponential functions? Exponential functions are in the form of f of x equals a to the power of x, where a can't be 1 and it's larger than 0. We want to find the derivative, and so we are going to go with the definition. F prime of x is the limit as h approaches 0 of f of x plus h minus f of x over h. And so if I plug in here, I get a to the power of x plus h. The other one is straightforward. Now, notice this means a to the power of x times a to the power of h, and a to the power of x is in common. I can take it out. Also, the limit pertains to h. I can take a to the power of x because it's independent of h. So now I have the function f of x is a to the power of x, and f prime is itself a to the power of x times something. The limit of a to the power of h minus 1 over h as h approaches 0. Look at this. This is some number. So if we could find some a such that this goes to 1, that'd be amazing. So is there an a such that this limit equals 1? Why is it amazing? Because the function and the derivative become identical. So the numerical analysis will result in the answer. So they work on different numbers, for example, 2 and 3. And by the way, again, you want to take the limit, you let h go closer and closer to 0. And they notice that for 2, we get to almost 0.7 or 0.6 now. They do that to number 3, and they get to 1.1. Okay, so we didn't get the 1. What did we get? We don't have the answer, but for sure, if 2 results in 0.69, 3 results in 1.1, there must be a number between 2 and 3. In fact, closer to 3 than 2. And you probably remember it's 2.718, and it continues indefinitely. So now we are going to define as follows. E is the number such that the limit of e to the power of h minus 1 over h as h approaches 0 is 1. So that's the way to define it now. Okay. Furthermore, the number E, also known as Euler's number, was first discovered by mathematician Jacob Bernoulli in 1683 while studying compound interest and popularized by Leonard Euler, who gave it the letter E as its symbol. Hence, it is often called Euler's number. Now, a couple of things I want to remind you. Geometrically, what does it mean? This means that of all possible exponential functions of the form y equals e to the power of x, the function f of x equals e to the power of x is the one whose tangent line at 0, 1, the y-intercept, has a slope f prime of 0. That is exactly 1. So take a look. Here's the function 2 to the power of x. This is 3 to the power of x. And here's the e that is in between. And if you draw a tangent line, okay, the slope is 1. One way to prove it, just differentiate this is e to the power of x, plug in 0, and you get 1. The other, but we haven't got there yet, supposedly. So here's how we approach it. If f of x is this and f prime is this, we're going to replace the x with 0 and see what happens. So if we replace the x with 0, f prime, it becomes f prime of 0. It becomes 8 to the power of 0, which is 1. And you get the limit of 8 to the power of h minus 1 over h as h approaches 0. Now, if instead of 8 to the power of x, we have e to the power of x, okay, so in general, f prime becomes f prime of 0 times 8 to the power of x. That's the relationship. Now, for e to the power of x, f prime is f prime of 0, e to the power of x, and f prime of, if f prime is also e to the power of x, then f prime of 0 must be 1. And these are the ones we have looked at. The limit of 1 plus 1 over n to the power of n as n approaches infinity, or the limit of 1 plus h over to the power of 1 over h as h approaches 0. And we know the number. Now we have this new definition. E is a number such that this limit of e to the power of h minus 1 over h as h approaches 0 is 1. What do we need to know? If f of x is e to the power of x, so is f prime of x. That's all we need to know. I just wanted to, of course, justify how we arrive at it. Okay, that's important, everybody. But just in case, what do I need to know to move on is the fact that the function and the derivative are identical when we choose e to the power of x. That's all there is to it. We want to differentiate where f of x is e to the power of x minus x, and I'm going to remind you that the derivative of x to the power of n is nx to the power of n minus 1. E to the power of x is itself, sine is cosine, cosine is negative sine. Therefore, this one is itself minus 1. Done. But they're asking for f double prime. And what is f double prime? Higher derivatives of f of x. The derivative of a function y equals f of x is itself a function y prime equals f prime of x. Therefore, you can take the derivative of f prime of x referred to as the second derivative of f of x, f double prime or f superscript 2x. This differentiation is not the exponent, okay? This differentiation process can be continued to find the third, fourth, and successive derivatives of f of x, known as higher order derivatives of f of x. Because prime notation becomes cumbersome for higher orders, we use the subscription notation f superscript, my apologies, f superscript n to denote the nth derivative of f of x. So just for the sake of argument, everybody, if I said f prime and then f double prime and then f triple prime is fine, then it becomes crazy if I want to go further. That's why for ultimately higher derivatives, they use the superscript. And again, we don't want to mix it up with exponent, okay? It's not the exponent, so be careful with that. So superscript, that's why it's inside the parentheses. And we're done. Now we want the second derivative. So if I want to differentiate this, it's itself, and this is 0, so just e to the power of x, and I'm done. We want to differentiate y equals sine t plus pi cosine t, so we are going to do term by term. The derivative of sine is cosine, so y prime is cosine. The derivative of cosine is negative sine, so plus pi times negative sine, which makes it minus pi sine t. All right, let's work on this one. To differentiate this, we're going to change this one to t to the power of 1/4. This one you can leave it unchanged, or minus 1/2 cosine t, so it becomes clear what we are doing as far as the differentiation is concerned, okay? It's really your choice, but in any event. Having said that, let's do it one by one. Now we are differentiating this 1/4, t to the power 1/4 minus 1. This one is itself. This one, negative 1/2. Cosine becomes minus sine. So minus sine t. And again, I want to emphasize that this is it. You're done with calculus. There's really not a lot of steps when it comes to calculus. There's only one step now. We are going to use algebra to finish the job. So this one, 1/4 minus 1, negative 3/4. And so we are looking at 1 over 4 t to the power of positive 3/4. So that becomes this becomes the fourth root of t cubed. This is itself, and negative positive 1/2 sine t. And if you want to put it in this format, so 1 over 4, the fourth root of t cubed, minus 4 e to the power of t. And this one, I just put it in the same format, plus sine t over t. Not that you have to, but you know, it's, I guess it's helpful. I hope you remember this question. The distance in meters of an object from a starting point is given by s of t equals 2t squared minus 5t plus 40, where t is time in seconds. What is the velocity of the object from 2 to 4 seconds? It was in feet when we did before. So simply s of 4 minus s of 2 divided by 4 minus 2. That's average velocity, total distance over total time. S of t sub 2, which is 4, minus s of t sub 1, which is 2, and it will do the job. Now you're going to plug in 2. We've done that already. 2 times 4 squared minus 5 times 4 plus 40. And then you plug in 2. 2 times 2 squared minus 5 times 2 plus 4, 40. And this simplifies to 52. This one to 38. 52 minus 38 is 14 halves 7 meters per second. What is the instantaneous velocity and acceleration? This is the reason we wanted to revisit this. And what is the velocity after 6 seconds? We are revisiting this because now we don't have to use the definition, which means we are going to differentiate to find v. V is s prime, so just 40 minus 5. After 6 seconds, if I plug in 4 times 6, 24 minus 5, 19 meters per second. Acceleration. What is acceleration? Acceleration is the second derivative of the position function. A of t is v prime or s double prime of. That means differentiated again. And that's the application of higher derivatives if you do. So if I differentiate this again, I get 4, which is independent of t. That means if the answer is 4, after 6 seconds or 5 seconds or 2 seconds or 10 seconds makes no difference. It's 4. And the units are meters per square second. And the question is why this is the case. I want to quickly justify that. A of t is dv dt. And the velocity has the unit meters per second. T has it per second. Meter per second results in meters per square. Finally, when does the object reach a velocity of 31 meters per second? Set them equal. So you move this, you make it plus 5. This is 36 divided by 4. T is 9 seconds.